Welcome to the third episode in the Mobility, Accessibility, and Design series. We met with Amos Winter, a professor at MIT, who taught us a lot about how he uses design in his own research and how he does needs finding on the ground, traveling all over the world to talk to users and learn their stories firsthand.
Welcome to Biomechanics on Our Minds. My name is Melissa Boswell.
And I'm Hannah O'Day, and we're PhD students at Stanford University.
This podcast is brought to you by the International Society of Biomechanics.
It's
time for Boom.
Welcome to Boom, where we have
Biomechanics on our minds.
Boom.
Boom.
Boom, boom, boom,
Boom, boom, boom, boom.
boom.
All right. We are happy to be talking with Professor Amos Winter, who is an associate professor in mechanical engineering at MIT. Thank you so much for being here with us, Amos. We're excited to talk to you about your work.
It's a pleasure to be here. Thank you.
Amos, we love to start with this question about beginnings and specifically thinking about your beginnings. And we're wondering if you'd share what first got you interested in being a biomechanist.
Oh boy. Well, I think I have a unique origin story, I guess. So my research group at MIT focuses on technologies aimed at developing emerging markets. And one of the areas we work in is prosthetics. But my background actually started, I think I have two biomechanics portions of my background. One was my PhD was actually focused on underwater digging clams, razor clams.
Whoa.
And converting their digging mechanisms into like robotic applications, primarily for anchoring. So I actually, as part of my PhD, we discovered how this species of razor clam, and all razor clams do this, move their shell in such a way to fluidize the soil around them so they can reduce drag and dig very quickly and efficiently. So there was a biomechanics side of that, in that we had to understand how they moved and then look at how that influences the fluid, solid, and soil mechanics around them to induce that quicksand effect. So that got me a little bit into biomechanics. And then on the side, as a grad student, I worked on wheelchairs a lot. If you Google me, you'll see a bunch about this thing called the leverage freedom chair, which is this wheelchair that uses two levers to propel it. So you grab the levers with your hands, and on the push stroke, it propels the chair forward. Well, the design requirements for that device is we wanted a single device that could go fast and efficiently on rough terrains in developing countries, but also be small enough to use in your home. And it turned out to be actually a pretty interesting biomechanics problem of how to make that happen. Because we essentially needed to make a mountain bike for your arms, but we couldn't use mountain bike technology like a derailleur and a multi-speed gear set where you shift the chain between gears, because it wasn't really available in many places around the world. It wasn't robust. It was kind of expensive. So what we ended up doing was kind of a biomechanics trick in that we designed the lever system such that when you grab the levers, you can shift your hands up and down the levers to change your mechanical advantage. Mm-hmm. So if you're, say, going through mud, you grab high on the levers, get a long lever length, and produce a lot of torque, but still push at the same force and frequency that's comfortable for your body. But then as the terrain smooths out and you want to go faster, you could just keep pushing at the same frequency and force, slide your hands down the levers, and start pushing through a bigger angle every stroke, create a higher angular velocity, and go faster.
Kind of like changing the gears on a bike.
It is like changing the gears on the bike. However, instead of making the machine change its geometry to change mechanical advantage, we made the person change their geometry.
Right.
And so we exploited the biomechanical abilities of the person, both in terms of like force and power output that they can get from their arms and chest, but also their dexterity, right? That they can move their arms up and down the levers. So what created our research group was bringing together, I guess, the background in like applied engineering science that I did in my PhD on what was called the RoboClam project, with this vision of how rigorous engineering science can make an impact in developing and emerging markets. And so you bring those together and you get what's now the Global Engineering Research Lab, my research group, but you also get our prosthetics program. And that actually grew out of the wheelchair experience because I started interacting with a lot of disability organizations around the world. And one of them in particular, the Jaipur Foot Organization, which is based in India, in Jaipur, India.
Yeah.
And they're actually the biggest distributor of prosthetic feet in the world by numbers. I interacted with them on the wheelchair program. And through that engagement, we started talking about what else would you like to do to enhance your products. And they said, well, actually, I have one next to me. This is so funny.
Yes.
This is just random from a lecture I gave the other day. This is a Jaipur foot.
Wow.
I didn't plan this. I just had one next to me. This is the Jaipur foot.
Like a good biomechanist does.
They've been making this since the 70s, and it's a transformative product because it looks lifelike, it's flexible, it's cheap to make. However, it's made by hand, so there's a lot of product variability. It's rather heavy for a prosthetic limb, and it doesn't meet international standards. So they said to me, boy, it'd be great if we could make a new product that is mass manufacturable, it's low cost, meets the international standards. And so what was cool about that experience is at first we thought, boy, we'll just copy this architecture, but just make it so it can be injection molded and made, less expensively and mass manufactured. But as we looked into this problem, we started asking how would somebody go about designing the stiffness and geometry of the foot to induce the biomechanical response that they want? And when we started looking into that question, we realized that there really was no theory to connect the mechanical design of a prosthetic foot to the desired biomechanical response you'd want it to exhibit. And this opened up like a Pandora's box of research because we started asking, well, how could we make a passive structure that when loaded induces the motion that we would want a person to walk with? And so that's been a really fulfilling, journey in biomechanics and mechanical engineering. It's so funny that I have all these next to me. Like this is kind of our most recent architecture. I literally have this slew of old prototypes next to me that I used in a lecture last week. But this is an architecture, and there's so many things about this that I think are really interesting from a biomechanical and mechanical engineering perspective. So the geometry of this and the material choice and the stiffness that's induced from the material and the geometry is all designed such that when you walk on this and this foot feels the ground reaction forces that you'd expect a person when they load it, it bends in such a way to make a person's lower leg move through space and time extremely accurately compared to able-bodied biomechanics. And what's cool from a biomechanical standpoint of this is that one of the big insights that we had was saying, okay, we're going to forget trying to design a prosthetic foot like a physiological foot, where you have a rotational joint at the ankle. In fact, we did that a lot. Here's one of ours that has a pin joint at the ankle. It turns out, though, if you concentrate all the motion at a rotational joint at the ankle, you need such a high stiffness and high range of motion spring, because that's how our ankle behaves. And that's kind of a pain to make. Instead, we took a black box approach and said, okay, in this black box, if we apply loads on the bottom and want motion at the output, we don't really care what the inside's doing. And that really enabled us to create a foot architecture that behaves nothing like a physiological ankle. There's no ankle in this thing. It's a fully uniform, structure, homogeneous structure. But everything about it is bendy. And so when you load it, the whole thing is bending in order to induce extremely accurate both loading and motion as you go through a step. So that's a super long-winded answer to your short question, but that's kind of how I got into biomechanics, and particularly biomechanics of prosthetic limbs.
Well, it was fun to see that journey, though, from clam to foot.
Yeah, from clam to foot. And I certainly like biomimetics. But I'm an agnostic engineer. I wouldn't just say, oh, nature thought of a good solution, so we got to copy it. No way. This foot is a good example of it. Like, this performs nothing like a foot, but moves like a foot.
Yeah, that's so interesting. It kind of reminds me, too, when you said, clamstick so fast, it just reminds me of, being at the beach when I was younger and, seeing the wave, leave and all the little clams there, and then they'd all, disappear so quickly.
Yeah.
But then I'm glad that you brought up making the all-terrain wheelchair made, and you also included making use of bike parts and other materials that are easily accessible to the community that you're building it for. And we talked about this before the interview started, but I remember you coming to the University of Akron to give a talk on this, and just how inspiring it was to be able to make devices that are more accessible, overcome some of these major challenges for the users that you're designing for. And as you were describing it, you were talking about these different constraints, like cost and being able to go through different terrain. And I'm curious how you learn to design with constraints, and perhaps how that's continued to influence your research now.
It's extremely influential in our research. And I think constraints are actually really powerful drivers for innovation. So, the general story in every project that I work on is that there's a compelling problem in a developing or emerging market. People there want a solution that delivers similar performance as what we'd pay for in the US or Europe, but the price point they can afford is dramatically lower. And so we can't just simply adapt the solutions that we may have in the US. We really have to rethink from a fundamental level of, how can we deliver that very high performance at a low cost? And what I find exciting about that is that if you're successful, you don't have to be restricted only to a developing and emerging market. You can actually create high value solutions that can work in global markets. Really, all the projects we work on follow this process that's called reverse innovation, where you use developing and emerging markets to provide those constraints, drive innovation of high performance, low cost products, and then transfer them back to wealthy countries as well, and try to create product lines that deliver value to both poor consumers and comparatively wealthier consumers. So the wheelchair has followed that course. It started as a developing world focused project, then morphed into a company called Global Research, Innovation, and Technology, or GRIT. It goes by the acronym GRIT. And so that is now a wheelchair that is sourced by the VA. It's the official wheelchair for the Spartan Games, which is the all-terrain obstacle course that people can run on, like through the mud and through obstacles. And it's become a transformative product for people in the U.S. too. And what's interesting, particularly when you're talking about people with disabilities, is that if you are physically disabled, it's very common to also be at a lower income level than able-bodied people. So even though a person may be living in the U.S., they still may be under cost constraints. And so our Grit Freedom Chair, which is the product that's sold in the U.S. market, is less than half the cost of other off-road wheelchairs. So it is priced where individuals can often be able to buy it out of pocket and benefit from it without reliance on insurance.
Wow.
So yeah, making a high performance, low cost product is typically beneficial to folks everywhere. And it's the same story with these feet that I showed you. I didn't show you. Here's a foot cosmesis and a high traction sole. We collaborate with Vibram, the hiking boot manufacturer.
Oh, yeah.
That's what this little octagon is. Same as what you have on probably your hiking soles. And then inside, there's the keel, the load bearing structure, that we've designed. And so this whole architecture is a fraction of the cost of conventional prosthetic feet that you'd find on the market. And this internal structure that I'm showing you, this is an updated version, but this is all made out of plastic. It's not made out of carbon fiber. So I can't tell you exact prices, but it's a pittance compared to what you would make out of a carbon fiber structure. But in our clinical tests, we've shown that mechanically, as well as with qualitative feedback, this performs as good or better than carbon fiber commercial products that cost orders of magnitude more money.
Wow. I love this idea of reverse engineering and really getting to be creative within constraints. Like that, I think I agree that can drive creativity. Sometimes I think about an analogy in if you have a school where students are forced to wear uniforms, they'll adapt how they're wearing them because they still want to be creative, but they're being creative within sort of this constraint. So I love that idea. And I'm wondering, you kind of just talked about being able to incorporate some qualitative feedback as well in these designs. They're very human centric. So I'm just wondering how you do that, maybe what resources or tips are important.
That's an excellent point. We have to very much not think just like technical engineers. I will often reflect on like the extents we'll go to map out like a socioeconomic ecosystem. It's just like such a crazy extent for a technical group, because we're a mechanical engineering research group, and the majority of our publications are around the physics-based engineering science that governs the behavior of our technologies. But as far as engaging that greater perspective of the problems we're trying to solve, it's critically important, and it's important that we map out not just the needs of end users, but really map out the constraints and requirements imposed by all the stakeholders that we're going to rely on to take an idea all the way to fruition. So it's very common for us to talk to funding agencies and manufacturing firms, NGOs, end users, like really everybody who's going to have a role to play in the dissemination of the technology. That is critically important. And I think, something I say in every one of my classes that I teach is that the single most powerful tool a designer can have is perspective. And in our line of work, perspective that goes way beyond our own perspective.
Totally.
The reason I say that is that the only reason designs ever fail is because they did not satisfy the requirements for the design. And oftentimes designers miss requirements, be it, economic or cultural or robustness. They're just not aware of them. And so the best thing you can do to try to ascertain those requirements is to put yourself in the shoes of the stakeholders and try to see the world through their eyes, through their perspective. So by actively recognizing your own ignorance and actively trying to seek the perspectives of your problem from multiple viewpoints, you best mitigate the risk of missing perspectives and thus missing design requirements. So yeah, we have to do it in every project we do. And as far as like maybe a more prescriptive process, what we'll often do is try to, if we have kind of an inkling of a project area, first thing we'll go to do is to go talk to a subject matter expert that knows that industry or knows a product line very similar to ours. So, in the case of biomechanics, the Jaipur Foot Organization, literally, they give out more than anybody else. And they will say things about, usage in the field or how people break them or the type of professions people may have, which will end up driving technical requirements, but we would have never known otherwise. Things like, this is another good example of engaging with stakeholders. Like when we test prototypes like this on people, all the time they'll say things like, yeah, it works pretty well to walk, but it doesn't look like a foot, and I could never wear it out in public because I'd stick out like a sore thumb. And that is what drives things like this, right? To get the skin tone right, in the features of the toes right, and knowing that people are going to step on slippery surfaces, so there's some tread pattern here to make sure, like on muddy surfaces, these aren't as slippery. And it's a high wear sole, because one of the failure points of this is people will wear through the cosmetic covering and actually get into the structural area, and then the foot will snap in half. So like all of this stuff is driven by stakeholder interactions. And yeah, I think this is a real case in point, because this white thing in the middle, that's largely driven by physics. And so we know loads in and we get motion out. But all the other stuff that this thing has to do is what drives, really the form and function of the whole product. I don't know if your podcast is put out visually as well as audibly. I don't know if these show and tells help or not.
It's very helpful. I think when we put it out, we'll put a little video clip of you showing those, so people can have a better understanding of what you're talking about. And funny that you just had them next to you. You're like, I didn't prepare it all, but I just had all of these examples of feet.
I really didn't plan it. No, I did a lecture on prototyping last week, and I have the whole series of prototypes. There's like 8 of them that led up to our most recent foot.
I've been really fascinated as you're talking about learning these different perspectives of the people that you're designing for. And recently, you've been working on a project investigating replacing draft animals with all-wheel drive motorcycles on small farms. So basically replacing the work animals on farms with motorcycles, and in doing so, addressing some unmet farmer requirements that were identified in interviews with Indian farmers. And so I'm wondering, as you were investigating that, and as you're saying, under better understanding their perspectives, was there anything surprising or unexpected that came about when doing that? I'm also kind of curious how this project came about anyway, because it's so different than, I guess like typical biomechanics projects. And yeah, the transition there seems interesting.
So to answer your second question first, how it came about, I try to keep my ear to the ground all the time, and connect with organizations that we may be able to work with. And in those interactions, what's always important is to explore where there's aligned value propositions, right? Is to understand what challenges are those companies facing, or other funding organizations. Like, what do they care about? What would like better look like? And try to understand what are some of the barriers that they're facing in order to achieve what would be better or what would enhance their organization. And often, if those barriers are technical in nature and mechanical engineering in nature, maybe there's something we can do about them. And that's very much with the case with the project you just mentioned on the little tractor. That came about through interactions with Mahindra, which is a big Indian tractor manufacturer. They also make cars and lots of other stuff. I actually connected with them through an office at MIT. It wasn't actually, I didn't connect with them through other contacts in India initially, but I went there and I did a few visits actually over a few years to understand where there are opportunities for your business. And one that stood out was in the farmer market that's still primarily using draft animals to farm. And they said, this is a market that's tens of millions of people, if not, hundreds of millions. It is hundreds of millions of people in India that are still using draft animals, and nobody's really selling powered equipment to them. We would love to do it, but, we're unsure of how to do it. And when this project started, their intuition was if they could sell equipment that reduced the reliance on manual labor by people, it could be really valuable. And that was a good assumption because there's an increasing shortage of manual labor in farming communities in India because there's this migration into the cities to have higher paying and kind of physically easier jobs. And so it's harder and harder for farmers to hire laborers to say like pick cotton or spray pesticides or pluck weeds. So the project actually started on how can you make a powered instrument that would replace human labor. But I think an important lesson that this project highlights is we can never rely on assumptions. We have to go in and understand like what does the ecosystem really tell us where value propositions could lie. So we ended up doing a series of interviews with a lot of farmers in target markets in India about their farming practices and about the economics behind their farming. What came out of that was so thought-provoking was that by far the biggest expense that farmers face is just keeping and tending a pair of bullocks or like oxen, draft cow-like, beings. And because every day they need to feed them, they need to hire somebody to look after them. Even when they're not working, they're still eating. And as we dug into the economics more and more, we realized that Indian farmers, if they just buy a pair of bullocks to only do farming, they will lose money. They have to do other activities to make money off them, like hauling goods to market or some other load carrying activities. So what we realized is that we could potentially make farmers more money by reducing that recurring cost in their farming practices by replacing the bullocks with a powered piece of equipment that only needs fuel when you need to use it. Otherwise, it's not really consuming any money. So that kind of set the fundamental requirements of instead of reducing manual labor, instead replace bullock labor with a powered piece of machinery. And what was also interesting about the human labor in farming is that the farmers still really needed to rely on humans particularly for activities that required humans' dexterity and perception. So, for example, when you're spraying pesticides, farmers want a person spraying them because instead of just like blowing pesticides all over the farm, you can reduce your pesticide usage if you spray it only in the places where it's
That
needed,
makes sense.
right?
Yeah.
So a sprayer can walk around and just spray it right at the right points on the plants, and you can lower your pesticide costs by doing that. So there's still a lot of operations that really utilize humans' dexterity and perception. So anyway, back to the bulky project. This, by the way, this project was termed bulky by Mahindra because they viewed this product as the key to unlock the bullock market.
Whoa.
So bulky is where it came from. So anyway, as we move forward in that project, one of the big technical challenges we faced was how to make a device that could create the pulling forces of a pair of bullocks, but still be low cost enough for farmers to afford. Why that's important is that the capital cost of tractors is really driven by material cost. And to create a device, a conventional tractor, that can match the peak pulling forces of two bullocks, it ends up being a rather heavy device and would correspond to a capital cost that's much higher than a pair of bullocks. So ideally, we want a price point that's near a pair of bullocks, but if we hit that, we'd end up with a lighter device than what should be able to generate the pulling force of a pair of bullocks. Right? So somehow we needed to create a lightweight and thus low-cost vehicle that could basically punch way above its weight as far as pulling forces that it could generate. And that's what created the research challenge of what we worked on. How do we generate very high pulling forces with a very lightweight device? And we accomplished this through a few physics tricks, actually. So the first was we adopted a platform of a two-wheel drive motorcycle. So basically all the load that's being exerted on the ground by the device is being carried through wheels that can also generate traction. And that's compared to a conventional two-wheel drive tractor where those two front wheels are supporting load, but they're not helping with traction. They're not driven.
They're not pulling.
Right? So they actually take away from the traction potential you could generate because the more it's just like any other frictional situation. The more vertical force you could generate, the more traction force you can generate, right? So by putting all the weight of the device on driven wheels, we could generate more traction. Then the second trick was that by putting the wheels in line with each other, so the front wheel is in line with the rear wheel, that front wheel ends up packing the soil for the rear wheel, and it makes the soil stronger. So the rear wheel can put more of a force on the soil before it slips. So that increased our traction forces. And then the real, I think, piece de resistance of the whole thing was using the plow, if we're pulling a plow through the soil, to generate downforce just like a wing does on a race car. So as the plow moves through the soil, it's pushing the soil upwards, which creates a reaction force to push the plow downwards. So that plow wants to dig itself deeper and deeper and deeper. And what that does is pull the vehicle harder against the soil and make it effectively heavier than it is. And this is the same trick that's used in race cars, that the wings on them create aerodynamic downforce to press the tires harder against the pavement so you get more traction when you want to go around a corner. So we exploited that same principle and created a lot of downforce and generated more traction. And so all of these tricks together resulted in a device that should weigh a little enough that it could hit the price point that we wanted to hit and creates as much or more peak traction forces as a pair of bullocks. So we were able to accomplish it. This comes back to testing with stakeholders too. So we did a series of tests that we called proof of physics tests to show that all our analysis was accurate and that this thing could actually generate the traction forces that we predicted. Then we did a series of proof of function tests. And this was kind of interesting too, because it was just logistically a nightmare to try to ship this thing back to India, particularly within the time span of a reasonable PhD. So what we ended up doing is a bunch of farming tests, doing all sorts of activities you'd want to use this little tractor for, hauling and spraying and rotivating and all these tilling activities. So we did those on a farm in Massachusetts, but documented them really well. And we asked feedback from farmers in Massachusetts about the performance, both farmers from the US, and there were some Peruvian farmers that worked there well, and they gave kind of a Peruvian perspective. Then we took all that information and brought it back to Indian farmers and did focus groups and talked about all the features and got their feedback. And the result of that was like, they were like, man, this thing's awesome. You know, it does the activities we want. They said they would pay a price point that was above where we wanted to set the price point, so that was good. So what I'm working on now is I guess refinements. What we had produced was really just a functional prototype, and now, you know, there's some ergonomics to be improved and like, you know, user interactions that can be improved, and that's what I care about and I'm working on right now.
That's an amazing evolution of that project. And I love how you talk about these tricks that you were able to incorporate to kind of achieve the objectives that you needed to achieve within your constraints.
Every single innovation that comes out of my group results from understanding the governing physics and gaining those insights of what variables we can manipulate to achieve our objective, and combining those technical insights with socioeconomic insights about how are users going to use this product. You know, what are their behaviors? What's their economic situation look like? And you blend those together, and they very much play on each other, because we'll so often have socioeconomic driven requirements that change our engineering decisions. You know, and when you blend those insights together, you get some pretty cool innovations that come out of it.
Yeah, for sure. And I think that's so important to hear and be reminded of as a biomechanist, when sometimes I feel like we're very good at one side of things, but not always the other.
I think don't be myopic, and the best thing you can do is recognize your own ignorance. You know, it's like, you probably know that famous Donald Rumsfeld quote about the unknown unknowns are what he worries about. The unknowns that he doesn't even know about, you know, and he doesn't know if they're going to, you know, bite you when you least expect it. I think when you can recognize your ignorance, you reduce those unknown unknowns. You put yourself in an active position to go try to figure out those unknowns by talking to other people who might know them, you know? And that's what we try to do all the time.
Well, thank you for sharing all of those stories and experiences. It seems like you've done a lot of iterative work, right? You've got 8 prototypes sitting next to you on the ground. And with a lot of that iterative work, I feel like there are little failures and lessons that you learn sort of along the way. So we're interested in if you could share a time where it felt like you maybe failed in your work and what you learned from it.
Well, I think another good piece of advice to every engineer is you will fail. Always. Nothing ever works exactly how you want the first try. And so if you know that, you can put yourself in a position to fail early and often and not catastrophically. And I would add to that in our line of work, fail early and often, not catastrophically, and do it in context with people who are best positioned to judge failure or success. Like in the case of developing world prosthetic limbs, it's developing world prosthetic limb users, because their perspective is going to be different than ours, and they're going to be clued into things that we would never know. In our work, we fail all the time for reasons we didn't anticipate. Like for example, we work on desalination of water, right? And we put all this effort into making a system that met World Health Organization standards of how much salt can be in drinking water, blah, 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 blah. And it was viable. It was, you know, it worked from an engineering standpoint. And as we kept developing it, our partner mentioned to us, you know, you got to make the water even less salty because of people's taste preferences. In India, over the last 20 years, people have become really accustomed to drinking very low salinity water.
Wow.
And they've developed a palate for that. That's what they like. And so even though that water is actually not necessarily as healthy for you as water with a bit more electrolytes in it, that's what they want. It was one of these situations where if we had not figured that out early, it could have been catastrophic, because our technology could have met all the specs by like World Health standards, but people would have rejected it because it didn't taste right.
Wow.
We come into those situations all the time, like in prosthetic feet. How the foot looks is extremely important, actually even more so than it would be in a US context. Because like you've probably seen, particularly I see it in veterans in the US, they'll walk around like in shorts showing off their prosthetic limbs. And they look It looks cool. It looks like kind of like Terminator-esque. It's like this super cool technology. It's like anodized aluminum. And culturally here, we don't look at them as like, a lower level in society because they're disabled. That's not the case in a lot of countries around the world. People with disabilities still face tons of stigma. And so that drives the design requirement in our work of trying to make people look as able-bodied as possible. And that's why we try to mimic able-bodied motion and biomechanics with our feet and how we tune the stiffness and geometry of our foot to generate that. But it's also how we design the cosmetic elements of the foot. So if you go into a mosque and you're praying, you don't stick out like a sore thumb because your foot does, look pretty lifelike in terms of skin tone and features. So all that is important. And we often realize a lot of those requirements by failing in earlier prototypes that didn't include those requirements. And we try to fail way before we're ready to commercialize. So we capture them along the iteration cycle of design. So when we are ready to commercialize, hopefully we've caught as many as we can.
I've heard the saying fail early and often before, but I really like this addition of in context. And I think it makes so much more sense too when you're able to give us these concrete examples of how much the context matters and getting input from the users. So thank you for sharing that with us. And before we ask our last question, can you share how people can learn more about you and your work?
Yeah, the best resource is to go to gear.mit.edu. Gear, just like a gear with teeth on it. That's our website. And GEAR is the acronym for the group, the Global Engineering and Research Lab. And on there, you can see our publications. You can see descriptions of our projects. You can see popular press articles about our work. So that's the best one-stop shop, I would say.
Awesome.
If you want to learn about some of the wheelchair work I've done, if you just Google my name, you'll see a TED Talk I gave a number of years ago, and that talks about the Leverage Freedom wheelchair and how that came to be.
Oh, that's great. Okay, we can include that link in the description of the podcast too. For our last question, I'm excited to hear your thoughts on what you're most excited about for the future of biomechanics and design.
So for the future of design, I am most excited about tackling global challenges, like climate change or water and energy. I really like those multidisciplinary problems. And I think this ties into pedagogically what I like about design is how do we continue to train subject matter experts while keeping their eyes open to fields that will influence their work, but they're not experts in, right? So I think about, in academia, I think about all these intellectual juggernauts around me that have this brain power that is really there to change the world. But so oftentimes people, I think, are stymied in being able to do that because they don't necessarily have the full context around the problems they would like to solve, right? So I can't look at maybe like a chemical engineer working on the latest and greatest like battery technology and rely on them to understand the usage practices of a battery that's running like a solar lighting and TV and irrigation system out in rural Kenya, right? But those design requirements of those usage practices could very much influence their innovative thinking and maybe trigger them to create a brilliant insight and solution that could solve that problem in the developing world. So what I think about a lot is like how can we instill maybe not even knowledge, but cognizance of unknown unknowns in people from many different subject areas. So they go into innovation being like, okay, I'm bringing some major tools to the party of innovating in my subject area, but I just need to be mindful about this other stuff I may need to think about if I want to translate my innovations to the real world. Like that's really where I care about teaching people about design and trying to grow the innovation capability of our society. Because otherwise, we can end up playing darts in the dark, right? Which I think is unfortunately how a lot of innovation happens, is that we come up with this great idea in our narrow subset of skills, in our subject matter area. We work on it in the lab for 10 years. And only at the end are we going to be able to ask questions of like, does it cost, the right amount for people to buy? Does it smell weird or not? And so are people going to reject it? Like, the way I frame these things are secondary requirements. I feel like engineering, and particularly academic innovation, is really good at focusing on primary requirements, things like efficiency and weight, and like the big glaring areas of improvement. But those secondary requirements, which are often the make or break of adoption of like user preference or cost or robustness or repairability in the field or supply chain or manufacturability, those aren't captured oftentimes in like really ground up innovation. And so as a designer and a teacher of design, I want to help really everybody just be cognizant of those things. You don't have to become an expert in them, but if you just know that they're there, it makes you more likely to go seek them out and seek out the information. And when you do, it will influence your innovation, and more likely guide it towards something tractable. So that's what I'm most excited about in design.
It kind of reminds me back when like we were in, I was in grade school and like you'd be doing a math problem and it would be some kind of word problem and scenario and you get an answer and your teacher would or my teacher would always ask like if it made sense to us. Like, does that make sense in the context of the problem? And I think being able to do that on a larger scale with all of these different problems that we're talking about and all of the amazing expertise and knowledge that, we do have either across people or, among certain people, is just really inspiring and amazing. And thank you for that answer. I don't think we've had one like that yet. So it was super insightful.
And why this is critically important in the coming decades is look at the problems that the world is facing, right? Mm-hmm. Like just take climate change for an example. If you solve climate change from a myopic standpoint of a single discipline, let's say we make everybody drive electric cars. Oh my God, that's got so many technical issues associated with it. Or it's like, okay, we force everybody to be a vegetarian. There's going to be a lot of pushback from like a cultural side and a preference side. And so we can't think about these myopically from single disciplines. And the balancing act we somehow have to strike is not watering down deep insights that come from specialization. Right? We need crazy, in electric cars, like battery experts and infrastructure experts, but also policy experts, and economics experts. So somehow we have to bring together multidisciplinary teams and make them aware of each other and the effects on each other, while not creating generalists that don't have the deep discipline insights to create the innovations in their disciplines, right? So it's this balancing act of like, I guess maybe in the ideal world, we teach a robot like every piece of information and they can aggregate it together and solve our problems. But I don't think humans have the capacity to do that. So I can't rely on like teaching a policy person like all the details of mechanical engineering. But what I can hope for is a policy person thinking about, a climate change initiative is going to have a technical side of it. I need to be aware of that. And maybe I need to reach out to somebody, maybe like me, who can think about the engineering side, and same vice versa with me. I can't think from a purely technical perspective. I need to reach out to the policy side too, right? So it's this balance between deep subject matter expertise, but bringing together information so you can come to a generalized solution without creating worthless generalists. That's what I mean.
That's it's really enlightening and just inspiring. And I'm really excited to share these ideas with other people. I think it'll be really influential for other researchers to hear these ideas. So thank you for talking about them. And thank you for being with us and taking the time to talk about your work, but also these really powerful sort of principles that guide it and make it so impactful.
Thank you. Well, it's a pleasure to be here. And thanks for inviting me, and it was fun talking about all this stuff.
Thank you for listening to Biomechanics on Our Minds. I'm Hannah.
And I'm Melissa. Thanks to the International Society of Biomechanics for supporting the podcast and to Peter Washington for creating all the music you hear on Boom.
Make sure to follow us on Twitter at BiomechanicsOOM and on Instagram and Facebook at Biomechanics on Our Minds.
If you have feedback, suggestions for guests, want to share new biomechanics research or research fail, want to host your own episode or be involved in the making of Boom, or just say hi, you can reach out to us at any of our social media platforms or send us an email at biomechanicsonOurminds@gmail.com.
Biomechanics off our minds.